All right, so let's look at the beginning of your notes. And let's look at example 1. You might have run across, when you did your homework, a question that looked like this. Well, I don't know, x equals y to some power, like y squared, y to the third, y to the fourth, y to the seventh, y to the ninth. True? So let's ponder this for a moment. Let's just look at x equals y squared. If I were to look at x equals y squared, if I were to put that in my calculator to graph, how would I get y by itself? I would take the square root of y squared, true? And when I take the square root of the other side, in order to get both answers, I have to do a plus or minus. So doesn't y equal a positive square root of x and a negative square root of x? Right? So let's put that in the calculator. Remind me to change the attendance, because otherwise it'll be wrong. So let's go up here, and I'm going to have to actually put in both the square root of x in one y equals, and then the second y equals, I'm going to have to do negative square root of x. Get the glare off of there. And then when I hit graph, you'll see both parts. There's the first one, and there's the second one. So let me ask you this. Is that a function? No. Why? It doesn't pass a vertical line test. So when you have the equation solved for x, make sure that you pay attention to the exponent. Anytime you have an even exponent, 2, 4, 6, 8, when you take the root of both sides, you have to do plus or minus, because even roots, you could take a negative up to an even root and still get a positive value, correct? But if you have an odd exponent like 3, 5, 7, 9, etc., when I take that root of both sides, we don't have to do plus or minus. So for instance, if you had x cubed equals 8, when you take the cube root of both sides, you don't do plus or minus cube root, because the cube root of 8 is 2. It's not negative 2, is it? Because negative 2 times itself 3 times would give you a negative 8, not a positive 8. So my point is, when you take even roots, you do have to do plus or minus. When you take an odd root, there is no plus or minus. So let's just look at what would be if I had x equals y cubed. How would you solve for that? How would you get y by itself? Take the cube root. So we take the cube root of y cubed, that would give us y, and I would have to take the cube root of x. There's only one answer to that. Y is equal to the cube root of x. So if I put that in my calculator, let's see if this is a function. So I'm going to clear out both of these equations. So to get your cube root, go to your math button. Oh, I guess there's an exact cube root. I'll just do it this way. Is that a function? Yes. So your odd roots are going to look like that. So my point is, when the question mark is even, it's not a function. So your answer to those questions are going to be no. When the question mark is odd, it is a function. So that's only when you have x equals y to some power. Does that clear that up? Because I'm assuming you had questions on that. All right, so then let's scroll forward. Can I move this? So let's flip all the way to, we stopped at increasing and decreasing functions. Is that
Yes.
correct? Okay. So this should be fairly straightforward. Should be. But let's look at increasing and decreasing functions. So an example of an increasing function might look like what we just saw with y equals the cube root of x. When we look at increasing and decreasing, we always go from left to right on the graph. We focus on the x-axis, but we look at what's happening to y. As I go from left to right on the x-axis, y starts out low and it gets higher and higher and higher and higher and higher as I go to the right on the x-axis. A decreasing function might look like this. As I go from left to right, y is decreasing, decreasing, decreasing. It's shallowing off, but it's still decreasing. Then you can have a constant, and a constant just means that there is no change in y from left to right, so it would be any horizontal line, anywhere. And then there are some graphs where you have both increasing, decreasing, and a constant. So I want you to put a point at -2, +2, and a point at +2, +2. And then we're going to show a decreasing here, straight line here, and an increasing here. So I've written in interval notation that the graph is, as I go from left to right, the graph is decreasing starting from, what's the leftmost point here? -infinity until I hit, boom, this point here, which on the x-axis separates the interval. Even though we're looking at the y-axis, the x-axis separates the interval. So this point here is -2. So from -infinity to -2, that graph is decreasing. And we are going to include -2 because it is part of that turning point, so to speak, if you will, of where it goes from decreasing to constant. And then from -2 to this point here, which is +2, we have a constant. There's no change. So we include both -2 and 2. And then from -2 to +infinity, we have an increasing function. And so it's shown looking like that. Not too hard, right? All right, so let's look at some examples. So turn your page. Then all I did here was list out the words of what we just said. And here's the important part of it. Because I could ask you this in words, you've got to be able to describe it to me. A function is increasing on an interval if for any 2 points in the interval a positive change in x, that just means I'm going from left to right, which is what we've been doing, results in a positive change in f of x. Isn't f of x your y? And that's what we're looking at, what's happening to y as I move x along in a positive direction. Yes? Mm-hmm. So long, you can paraphrase, and you can use your own words so long as what you say is accurate and you get your point across. I don't believe in regurgitating most things word for word. And then your function is decreasing on an interval if for any 2 points there's a positive change in x, meaning I'm going from left to right, but there's a negative change in f of x, which is your y. And of course we have a constant, which means there's no change, 0 change. So let's look at example 6. They're going to ask you what interval or intervals is the particular equation that they've given you, increasing, decreasing, or constant. So we've got to graph it. So go to y equals, and we're going to put in parentheses x plus 2, and then squared. And then graph it. I know why the voice is so low on here. That's so loud. But they tell me my air conditioning is working just fine. All right, so this is a parabola that has its vertex on the x-axis at -2, 0. It crosses the y-axis at +4. I'm saving you time from having to find these. And because this is the vertex, the axis of symmetry goes through here, so there's a symmetrical sister point right there. So there's your quick sketch. Anytime we have a relative minimum or a relative maximum on a graph, that is your turning point. Something's happening to increasing, decreasing, or a constant. And that turning point is going to be part of your interval. So since that point is -2, the leftmost point is negative infinity. So from negative infinity to -2, what's happening to the graph? Is it increasing, decreasing, or constant? It started high and it went low for y. So doesn't that mean it? Don't think in terms of x, we're thinking in terms of y. Even though we're using x for our interval, it is decreasing, isn't it? The graph is going lower. So we are decreasing from negative infinity to -2, and we do include -2. Then from -2 to positive infinity, what's happening? We are increasing. Whoops, and so we're going to include -2 and go to positive infinity. That's not so bad, right? This graph is a little bit more interesting. So let's go ahead and put that one in our calculator. So we have x squared divided by, in parentheses, x squared minus 1. If you don't put the whole denominator in parentheses, your graph won't look like mine. We will eventually get to horizontal asymptotes. So I'm going to show you how to find those, but for right now, you do know how to find the vertical asymptotes. We talked about that yesterday. So this is restricted, correct? So if we set that not equal to 0, that means that x squared cannot equal +1. I'm solving algebraically. And then take the square root of both sides. I have to do plus or minus the square root of 1. Turn that phone off. X is equal to positive or -1. Oh, thank you, cannot equal. So that means I have a vertical asymptote at 1 and -1, which is what you're seeing on the graph. See how distracting that phone is. Then what you don't realize is we have a horizontal asymptote. You can see this graph is approaching a number. What number does it appear to be approaching? What do you think that number is? It's actually +1. So it's approaching +1. So there's a horizontal asymptote there. I'll show you how to find those later. And the graph itself does have a vertex at 0, 0, and it's just hugging these asymptotes, so it's really narrow. And then it's hugging these asymptotes up here and here. So are there any turning points on here? Yeah, the vertex of the parabola, right? So this is a turning point. And then each of your, because we're talking about the x-axis, each of your asymptotes, the vertical asymptotes, are fences that have to be jumped. So they are part of your intervals as well. So this point here at -1, and this point here at +1, and this point here at 0, they're all going to be part of our intervals because we have a turning point here and we have vertical asymptotes that are fences. So my leftmost value is -infinity, my rightmost value is +infinity. True? So let's start from -infinity and we hit the fence. What is happening from -infinity to this fence? What's happening to this graph? It's increasing. So we have an increasing graph from -infinity to that fence is -1. Do we include the fence that we jump? Does the graph ever touch that point? No. Remember, x cannot be -1. So unlike the last one, turning points are included. Fences not included. So then from -1 to 0, because I hit a turning point. So what's happening to the graph from -1 to 0? We start low and we go high, so it's actually increasing. Don't go backwards, because if you go backwards, you're going from right to left. We want to go from left to right, so we start low and go high. So that also is increasing. So union. Do we include -1? No, it's a fence. Do we include 0? Yes, it's part of the graph. It's an actual point on the graph, so it's a turning point. Then from 0 to this next fence, which is 1, what's happening? We start high and we go low, so that's a decreasing. Do we include 0? Yes. Do we include 1? No, it's a fence. So we hop the fence and we go from 1 to infinity. What's happening to the graph? We start high and go low, so what's happening? It's decreasing, so that's a union here. We're going from 1 to infinity, and we don't include 1 because it's a fence that we jumped. Does that make sense? That was a harder one. So you're looking for fences, and you're looking for turning points. Yes? Say that again? In the y equals? Did you put parentheses around your whole denominator? Because if you didn't, what it's going to do is probably not show anything. Did yours not show anything? Because it's probably 0. Y equals 0, which would be the x-axis. Is that better? Let me see your calculator. Oh, it's because of your asymptotes. So he's got the older calculator, and so it looks like on his calculator that that part of the parabola is not showing up, and that's one of the arguments why they took the asymptotes out on the newer calculators. You can kind of see the graph starting up here, but because it hugs those asymptotes so close and it's so narrow, it actually is showing up. It's hard to see. So you have to learn to love your calculator and understand what it's doing. So you did everything right. Okay, so any other questions on that? Let's talk about boundedness. Now, there is a part on the boundedness that I disagree with your textbook only because there's no reasonable answer to it, and I have asked around, and nobody else agrees with the book either, which doesn't mean that we're right and they're wrong. I just have more research to do. So I'm going to show you what I'm talking about when you do your homework and how to answer that so that there's not an issue. But let's just go ahead and look at boundedness because I find it kind of funny. I already talked about that. I find it kind of funny that your book says that boundedness is fairly simple to understand. Well, it is, except for in one case. And so we'll have to figure out the reason for that. So let's take what we looked at here, and we're going to draw something similar to that here. So just draw a parabola going down here, and we're just sketching it, just for a sketch. So in order to explain to you what bounded means, I've got to talk about the first two examples first. So this graph is not considered bounded above or below the graph. In other words, as I go from left to right, this part of the graph is increasing without bound, meaning up to infinity. Here, it's increasing and then decreasing without bound, and here it's decreasing without bound, meaning there's infinity to parts of this graph. Whereas over here, I'm going to give you an example where it's not bounded above, but it is bounded below. So put a graph that looks something similar to this. When we talk about boundedness, we want an above and below. Above and below means that our focus is on the x-axis. This graph is not bounded above, but it is bounded below. Do you see why? This is the part of the graph that is below the x-axis. Doesn't it have a definite start and a definite end all below the x-axis? Whereas if you look above the x-axis, is there a definite start here? No. There's not a definite end here. So anytime you have infinity parts on that graph, it's not bounded. No infinity parts down here, so it's bounded below. It's not bounded above. Does that make sense now why this one is not bounded on either? Okay, so let's turn the page. Let's look at these two examples. So bounded above, but not below. So let's flip the example that I just showed you. So this is just an example. So again, here's the x-axis. This is the part that is above the x-axis that has a definite start and a definite end. So it's bounded above. But below, we have points of infinity on that graph. So it is not bounded below. Then we have a graph that's just plain bounded. Not above or below, it's just totally bounded. And what that means is there are no parts of infinity on this graph at all. This graph has a definite start and a definite end. Even though this is our x-axis and we have the graph is bounded both above and below the x-axis, because it's bounded both above and below, it's considered just bounded. So the assumption is it's bounded both above and below. So that seems fairly straightforward, yes? Well, until we get to a particular example. So before I get to that, let's talk about example 7. So they're going to give you an equation and you're going to graph it. So go to your calculator. We're going to graph it, and we've got 3x squared minus 4. Should be what kind of graph? Parabola. So this is a parabola whose vertex is at -4, and we're just going to sketch it for time purposes. If you're doing a test, I would expect you to find the zeros, right, and be a whole lot more accurate than I'm going to do right here. So in relation, here's your x-axis. Is this graph bounded above, bounded below, or just bounded, or neither? It is bounded below. Very good. You're thinking piece of cake, right? Maybe. So this one, make sure when you put this fraction in that you put parentheses around the 1 plus x squared. So we have x, x divided by parentheses 1 plus x squared. Kind of hard to tell what's happening on that graph. So what should I do? There you go. So I'm going to hit trace first. I want my cursor to be where I want to zoom in, and it happens to be at the origin, which is a great place. So we're going to hit zoom in and enter. Now we can see what's happening. So we have kind of a loop, and then isn't it coming back towards the x-axis? And if you're not quite sure, we can hit trace and we can cursor to the right and just see what's happened to the right. It's a little slow. And then what your calculator is going to do is it's just going to keep moving to the right. Am I getting closer and closer to the x-axis? Do you think it's ever going to cross the x-axis? What's happening to y? It's getting smaller and smaller and smaller, but is it ever actually getting to 0? You're waiting for it. You believe it's going to cross, don't you? It's not. So I'm going to stop. So I'm going to zoom standard. Let me just tell you that there are ways that you can do it algebraically, and your book will show it to you. It's not in your homework, and I'm not going to for this course. If you're an honors level course, then I'd make you do it. But for this course, we're not going to. So assume I'm not going to give you one that, way out at 1,000 or what time to cross. Right? Okay. So I'm going to trace, I'm going to zoom back in just so that we can draw this graph. And I'm going to exaggerate a smidge. So we have a point, it obviously crosses at 0, 0 because x can be 0. There are no restrictions on x. The denominator cannot be 0 with 1 plus x squared. And it has this loop, and then it comes back down. Then it has this loop here, and it comes back up, but approaches the x-axis from the bottom. So looking at the x-axis, do you consider this bounded or unbounded? Yeah. I would say not bounded, or neither, or none, however. Then we come to an issue. So we're going to use this space here that's down here only because we have the room for it. So we're going to graph the following, and here's what's going to happen. You're going to come to your homework and you're going to go, oh, this makes perfect sense, until you answer this particular question. There's like 2 or 3 of them. You have y equals 1 over x, or some number over some x to a power. Okay? So let's just plot 1 over, I'm going to do zoom standard again. Let's plot 1 over x. Seems innocent enough. What's it hugging? The x and y axis. So it's over here and over here. What would you say that graph is? Bounded, unbounded, above, below, what is it? I'd say it's unbounded, right? It's not touching the x-axis anywhere, is it? Nor will it. X cannot be 0, therefore y cannot be 0. Here's what your book is going to say, that under certain intervals we can consider it bounded or unbounded. And so what they're going to say is from negative infinity to 0, and it's in parentheses because we can't include 0, they're going to say that it is bounded above. Is that part of the graph even above the x-axis? Do you see my confusion? Then they're going to say over here, from 0 to positive infinity, what do you think they're going to say? Bounded below. Which, again, I'm like, huh? I mean, you can change the graph to be like, let's just change it to 5 divided by x squared. So it'd look like that, right? Same thing. It's a very similar graph, but what if I did 5 over, I did x, that's why it looks the same. Let's try this again. 5 divided by x squared. I knew it was supposed to look different. There it goes. It flipped it. Weird, right? So that doesn't look the same as this one. They're going to say that this is probably bounded below, and this is bounded below. So play with it. But I wanted you to get the right answer, even though we don't understand the answer. I will research it further, and I will come up with an answer that either the book is wrong, which I highly doubt, or there's a reason for it that they haven't explained. I've never come across that before. And neither have the other teachers here, so we'll see. But do bear that in mind. So take all of this and draw an arrow up to this section. And you can put question, question, question. Don't know why. All right, so then we're going to talk about local and absolute extrema. So those are the peaks and valleys of a graph. So like the vertex is a absolute extrema. I've been calling it a what? Relative max or min. So even though local and absolute extrema are called local maxima or local minima, it is also known as relative max or min. And that's typically what you'll see me referring to them as. When you get to calculus, there's some very specific differences, but for now, this is what we're going to call them. All right, so flip your paper. Let's look at example 8, and we're just going to find the relative max and mins on the next graph. So you're to decide if this function has any local max or mins, and then find them. Now, pay attention to how they're asking the question. Technically, the local max or min is just the y value, but oftentimes, like this one, they'll say, find the local max or min and the value of x at which that point occurs. I will typically ask for it in an ordered pair, but depending upon how they ask their question, MathXL depends upon whether they want just the y value or the ordered pair. Here they want the ordered pair, or they might list it out separately, and it'll be quite obvious on MathXL. All right, so let's go ahead and plot this in our calculator. So x to the 4th minus 7x squared plus 6x. Is this an even, an odd, or a neither function, by the way? If you put in a negative x, will it change all signs, keep all signs the same, or some signs change and some signs stay? Put in a negative here, it stays the same, right? Put in a negative here, it stays the same, doesn't it? Put in a negative here, what happens? Changes sign. So these two stay the same. That one changed. So it is neither even nor odd. And as you look at the graph, it is not symmetric to the origin or to the y-axis. So therefore, it's definitely not even or odd visually. So this is a lovely little loop-de-loop. At most, how many times does it cross the x-axis? Because it's a degree 4 polynomial, right? So let's find the zeros first. That's the easiest place to start. So we're going to find our zeros first. So second calc, 0. So scroll left. We're not going to be able to see this dip here. You could do zoom fit, but I wouldn't for right now. I need my cursor above the x-axis. So when I move just one click above the x-axis, I can no longer see it. So just have faith it's there. Hit enter. And then below, hit enter. And we get negative 3, 0. The next 0, scroll to the right, enter, go just above, enter, enter again. 0, 0, not shocking. Then the next 0 is here, so second calc, just above, enter, and bless you, just below. So we get 1, 0. And our last 0, enter, enter, yes, 2, 0. So those are all the places that it crosses the x-axis. So then I like to find my max and mins from left to right so I don't forget any. Leftmost is this one. Is that a max or min? It's a min. So let's do second calc. You're going to select minimum, 3, and you want to be to the left of that minimum. So right now my cursor is here, so I'm scrolling to the left. You can look at your x to see who disappeared. The closer you are to that dip, the better off you are, but on this particular one, it's really hard to get close to that minimum dip because you can't see it. You could zoom out to see it, but in this particular case, we should all get the same answer. So I'm going to actually go a little to the right and hit enter. And I'll know immediately by my answer if I went too far right. And I'm going to scroll until I see my cursor again. There it is. So I'm going to go down one more. So enter, enter again. Now if I didn't get a left and a right and a sign change there, that would tell me I had an error. So how many decimal places are we going to go out to? Nope. What's the agreement? 2. So this is a minimum. It is a relative minimum. And its x value is negative 2.6, and the y value is negative 24.06 again. All right, so we're going to plot that, but it's really hard to plot negative 24 on this particular grid, agreed? So we're going to do our best. I'm going to plot it all the way down here, even though it's not necessarily accurate, and we're going to label it negative 2.06, negative 24.06. All right, next we have a what? What's this one? Maximum. So second calc, choose maximum, which is 4. So scroll to the right until we're just to the left of that maximum point, hit enter. Scroll to the right some more, hit enter, and enter again. It's just like kind of a 0. So since this is a max, bless you, we've got 0.4 what? 6 and 1.32. And we're going to plot that. So it's about halfway to the right, and then a little over 1. I'm going to label that. And then we have one more, yes. Oh, shucks. Yep. Good thing. Thank you. I would have noticed that eventually. But I'm glad you're awake. So to the right and up, that's much easier. Okay. So then the last one is a what? That one's a what? Minimum. So second calc, minimum. Scroll right, enter. More right, enter, enter again. So we have 1.60, you'd have to include the 0, and negative 1.7 what? 7. So it is a minimum. So 1.60 and negative 1.77. So to the right 1.5 and down a little over 1.5. And now we have all the points that we need in order to connect the dots. So starting high and going low. You might want to write yourself a note here that relative maximum actually refers to the y value. So technically, this is really your relative maximum, just that y value. Good to go with that? All right, so let's talk about even and odd functions. So I put in here that to determine if a function is even, I'm telling you to put negative x in to the function for every x value. So if I put negative x into the function for every x value, it should have no effect on the function whatsoever. For instance, let's take f of x is equal to x squared. There's a key to the fact that the exponent here is x squared. If I take and I input into that function a negative x in for every x value, I should expect to see 0 sign change. I should result in exactly the same function as I started with. And f of negative x gives me a negative x times a negative x is a positive x squared. Did I come out with exactly the same function? Yep, no sign change. And even if I had tacked on a constant to this, like a +6 or a -7 or whatever, it still would be no sign change because putting in a negative x is not going to affect the sign of that constant. If we graph this, you're also going to see that it is symmetrical with respect to the y-axis. All even functions are. So if we graph this, I'm going to put in just x squared, which is a parabola. Its vertex is at 0, 0. And it's got the following points, which all that I've done is I've mentally plugged in values for x and squared them. So let's list out those values. So all I didn't put this one on there because it didn't fit. But if I took -3 and squared it, I'd get a +9. -2 squared is a +4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 is 4. And 3 is 9. What do you notice about all the y values? There's no sign change. Even though there's a sign change in x, there is no sign change in y. That is evidence of an even function when you're looking at a table of values. The other evidence when you're looking at a graph itself is that it is symmetrical to the y-axis. If it's symmetrical to anything but the y-axis, and remember parabolas in this case, parabolas, have a line of symmetry. You got to be able to cut that graph in half and fold it onto that y-axis. And if it lays onto itself, it is an even function. So there's 3 ways to determine an even function. Plugging in -x, no sign change. Symmetric to the y-axis. Table of values, if you change the sign of x, no sign change in y. All right, so let's look at one that is neither odd nor even. So how about one we did earlier when we first started? X equals y squared. Notice it's not in function notation because, is it a function? No, it's not a function. So I'm going to go ahead and graph it first. So let's choose some values. In this case, I'm going to choose values for y because it's easier to choose for y to find x. So if I take y and let it equal -3, if I square it, I get 9. -2 squared is +4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. So not all those are going to fit. And let's plot the points. So I've got -2, 4. Or I'm sorry, 4, -2. So I'm reading it backwards. 4, -2. 1, -1. 0, 0. 1, 1. 4, 2. Is this symmetric to the y-axis? Y-axis. Yes or no? No. But it is symmetric to the x-axis. So symmetry to the x-axis means it's neither odd nor even. So if you see a graph that's symmetrical to the x-axis, it's not odd, it's not even. And notice that when there was no sign change in x, there was definitely sign changes in y. So it's kind of weird change there. So neither even nor odd. And that's not that all neither even or odd are symmetric to the x-axis. This particular one is. All right, let's look at an odd function. So turn that. So we're going to do the same thing with the odd function. We are going to plug in a -x. So if I have f of x is equal to x cubed, notice that my exponent on the odd function is cubed. When I cube a negative, what happens? Well, something positive goes negative and something negative goes positive, doesn't it? Depends on what the coefficient is that's out in front. So if I take f of x and I replace every x in the function with a -x, notice that f of -x is equal to, if I cube a negative, I get a negative x cubed. Are these the same? No, notice that there is a sign change. Now, if I happen to have tacked on a constant onto this, like x cubed plus 6 or x cubed minus 7, there would not be a sign change on the constant. It would be considered not an odd function because all the term signs must change. So write yourself a note that all terms sign must change. Triangle means change. So you might also want to note on the previous page that for this one, for the even function, all terms signs must stay the same. So for an even function, all terms signs stay the same. But for an odd, everyone's going to change. So if there is ever a constant, even though all of the exponents are odd, there's not going to be a sign change on that constant. It's not an odd function. And do note that odd functions are symmetric with respect to the origin. And here's what that looks like. So let's go ahead and graph this. I'm going to change my exponent to 3. Let's look at the table of values and see what we're going to plot here. I've got x and y. There's some that I'm definitely not going to be able to plot. Not many of them. So if I choose a value for x, just choose -3. If I cube that, I get -27. If I choose -2 and cube that, I get -8. Choose -1 and cube it, I get -1. Cube 0, I get 0. Cube 1, I get 1. Cube 2, I get +8. And cube 3, I get +27, and so forth. What do you notice about as I change the sign of x, what's happening to y? Its sign is changing also. So unlike with the even function, when I change the sign of x, the y's sign did not change at all. And here's what this looks like. So I have a point at 0, 0. I can plot the -1, -1, and the +1, +1. If I were to try to attempt to plot the -2, -8, I'd be over here and like down here somewhere. So this is going to, is that increasing or decreasing, by the way? From left to right. Increasing. And then this one, same thing, it's going to end up going up like this. So what's happening is it's being reflected above the x-axis and it's being reflected over the y-axis. So symmetry to the origin is a double reflection. And it looks like you're going in opposite directions, sort of wonky directions. So you ought to be able to determine odd versus even by either substituting in -x, looking at the graph and determining is it symmetrical to the y-axis or the origin, or looking at your table of values. So look at example 9. Let's graph x squared minus 3. So this is a parabola whose vertex is at -3. And for time purposes, we're just going to sketch it. We're not going to look for the zeros right now, but you would normally. So what do you notice about the graph? Isn't this a line of symmetry? What does that tell you about the graph? It should be even. Also notice that you have an even exponent. So if I algebraically went and replaced every x in the function with a -x, I'm looking for no sign change for all terms if it's even. And so a -x squared is a +x squared, and the -3 doesn't change. Aren't these the same? No sign change. So this is an even function. And it's symmetrical with respect to the y-axis. Then look at B. So we're going to plot that. We have an even exponent, an odd exponent, and a constant, so that ought to be interesting. So I have minus 2x minus 2. Your buddy's here. Now that's a parabola also, right? Its vertex is somewhere over here, since we're running out of time. So go ahead and graph this. I want to say my vertex is at 1, -2, but I could be wrong. Anyway, is this symmetric to the y-axis? It has a symmetry that's moved off of the y-axis. Does that automatically makes it so it's not even? And is it symmetric to the origin? So it can't be odd. And look at the math behind it. So if I take every x and substitute in a negative x, look for what happens with sign changes. I get no sign change here for the x squared. The -2 times a negative x gives a positive x. I do get a sign change here, but the constant doesn't change sign. So I get no change, a change, no change. So that means that it is neither even nor odd. Now, I'm going to stop here, but because we're going to talk about the fraction ones tomorrow. Don't do the fraction symmetry ones because there's a little catch with them that you may not understand unless I point it out. So again, you're not going to be able to finish your homework. We'll have part 3 coming tomorrow.